All right, sorry I couldn't be here today, guys. I'm in a science steering committee for the district today. And so what you guys are going to do is keep learning about nuclear reactions. Okay, so we've been talking about fusion and that nuclear reaction and how it occurs in stars like our sun. And then in our last activity or investigation, we learned about some other types of nuclear reactions like beta decay, alpha decay, fusion, and fission. And so what we're going to do is we're going to take a look at the specifics, and we're going to look at what happens in each and how we can represent them with little equations. So what I'm going to do is kind of give you guys a heads up with this old gold activity and kind of get you started with it up here on screen so that hopefully it's more understandable for you guys. So before you guys did this, you played a little nuclear quest game, so hopefully you guys had a little fun with that, but also hopefully you learned something from it. Hopefully it kind of gave you a visualization to see that during beta decay, you always move one ahead on the periodic table. So every time you drew a beta decay card, you always skipped one ahead, right? And anytime that you picked up an alpha decay card, you always went two backwards. Okay, so those are the two main ones, alpha and beta decay. And then fusion, you always skipped way ahead because you made something bigger. And fission, you're splitting it apart, so you kind of always jump back to something perhaps a little smaller. All right, so this activity is going to give you some kind of a practice on using your periodic table and then also representing these different types of nuclear reactions using specific ways, specific equations, I guess, that we can represent them as. All right, so in part one, it's just kind of an atom review, knowing how to find on your periodic table the chemical symbol, the atomic number, okay, which remember, if you look at your periodic table, is the top number, right, in the box. That's the atomic number. The atomic number is the number of protons, okay? And we haven't talked about electrons because electrons aren't really, the electrons are not needed in nuclear reactions. But we know that all atoms are neutral, so that means positive and negative charges need to cancel. So number of protons is equal to the number of electrons. So whatever number you have for protons, that's going to be equal to the number of electrons. So for example, carbon looks like this, and it's on the periodic table. So this is the atomic number. Atomic number. It is also the number of protons and the number of electrons. It's a little E for electrons. Okay, so it should have the same number for B, C, and D. All right, average atomic mass or weight, that's that. Remember, it has to do with the isotopes. So different atoms are going to have different numbers of neutrons, so the weight is going to vary a little bit. All right, and then F is the number of neutrons for two isotopes. All right, so remember to round up and subtract. All right, so you're just going to subtract and round down, round this number down and subtract. So for example, for carbon, we would round up to 13 because 12.01 is between the numbers 12 and 13. So if we take 13 minus 6, we'd get 7 neutrons. If we round down to 12, 12 minus 6 is 6 neutrons. So you're going to do that same kind of idea with magnesium instead of carbon. Okay, and then number 2, make a drawing of an oxygen atom and label the electrons, the nucleus, the neutrons, and the protons in your drawing. So I'm going to give you kind of a skeleton and you're going to fill it in. So draw your nucleus in the middle and you're going to fill in however many neutrons and protons are on the outside. And then what you're going to do is you're going to draw a couple rings on the outside. And I'm going to tell you right now that the first ring only has 2. And you may remember this from middle school, right? 2, 8, 18. Okay, so there's 2 electrons in that first ring, and then you're going to fill in the other electrons in the second ring. Okay, we're going to go more over atomic structure early in the next unit, but hopefully it should be review from middle school, 8th grade science. Okay, so in part 2, here's where we're actually taking a look at nuclear chemistry and nuclear reactions. So there's some questions just to go over, you know, stuff that we've kind of covered in the last investigation and the last notes that you guys had to do with the reading. But let's take a look at this chart, this table to fill in. So you can see that we've got a nuclear equation on the left here. And then it says change in atomic number, change in number of protons, neutrons, change in mass, and then the type. So let's do the first one together. So we can see that it's radium with 226 is his mass and 88 is the number of protons. And we can see that it goes down and releases an He. Remember, that's our alpha particle. Our helium nucleus is an alpha particle. We saw that same particle when we were talking about proton-proton fusion in stars. All right, so it makes that helium-4 nucleus. So that's basically during this decay, we are releasing a helium-4 nucleus now. And it becomes Rn, which is radon. And that's 222. So if we take a look, this is like our before picture, and this is our after picture. So the change in atomic number, so that's the number of protons, the bottom number. Remember in our isotope symbol, okay, we had the top number is the mass, and our bottom number is the number of protons. Okay, so our atomic number is the number of protons. So we went from 88 to start with here down to 86. So that means we lost 2 in atomic number. Okay, because it flew out with our He. Okay, so that's where we lost 2. Change in number of protons. That's going to be the same number. These guys are going to be the same. Because atomic number means the number of protons. All right, change in the number of neutrons. Here we have to do a little bit of math. All right, we can take a look at our alpha particle for that. Right, so our alpha particle has a mass of 4 and it has 2 protons. So that means 4 minus 2 would be 2 neutrons. So in here we would put minus 2 neutrons as well. And then the change in mass, we can look at it one of 2 ways. We can subtract, we can look at radon and see what his mass started with, 226, and then he ended with 222, so that's minus 4. Okay, or if we can recognize that this alpha particle here is spit out during this, spit out of the nucleus during alpha decay, and so we know that a total mass of helium-4 is 4. So we can put change of mass as negative 4. And so anytime we release a helium nucleus from the nucleus of a different atom, that's always what we call alpha decay. Okay? All right. Let's do one more, C. So C is it's slightly different. This is 2 elements coming together to make a bigger element. And if you remember, that's exactly what happens in the middle of stars, right? It is basically we're taking an element and we're adding helium to it every time. That's our alpha fusion. All right, so this guy is fusion. And taking 2 elements and putting it into 1 element is fusion. So if we take a look, this is oxygen with a mass of 17 and fusing with nitrogen with a mass of 14. And we end up with phosphorus with a mass of 31. And so we can see here, this is actually super easy, that 17 plus 14 is 31, and 8 plus 7 is 15. So in a nuclear reaction, the top and bottom numbers need to be equal on both sides of the arrow. So that arrow is kind of like an equal sign. So the top numbers have to equal and the bottom numbers have to equal. In fact, it works with our first example too, right? 222 plus 4 equals 226. And 86 plus 2 equals 88. Okay, or if we read left, right to left. No, left to right, 88 equals 2 plus 86. Okay, so it's very, very simple math to figure this out. All right, so when we're looking at a fusion one, think of the first one as, kind of the beginning element, and then whatever gets changed, okay, is added is the second one. So for example, if we're looking at the change in atomic number, okay, we're going from oxygen that has 8 to phosphorus that has 15, so we've added 7. In fact, we can see that we've added 7 right here because nitrogen is plus 7. All right, number of protons, again, plus 7. Number of neutrons we added. Well, you could do one of two ways. We could see that 17 minus 8 would be 9 protons that we started with. 31 minus 15 is 16. Okay. So we've gone from 9 to 16, so that's plus 7. Okay. Or another way we can figure it out is nitrogen here has a mass of 14, and 7 of those are protons. So 14 minus 7 is 7. Either way, you're going to get the same answer. Okay. So here we've added a total mass of 14. 7 plus 7 is 14. Remember, the mass of an atom is always your protons plus your neutrons, equal mass. All right, we said earlier that this guy is fusion. Anytime you add two elements together to make a bigger element, that's what we call fusion. Okay, so you're going to use that same thinking and that same gist to fill in the rest of the table. Okay, so I'm going to take a look at the back side of your paper here, and then I'll leave the rest of the time for you guys to get going and finish this. All right, so on the back side of your activity sheet, you'll see that basically it's just a bunch of nuclear reaction equations that you have to fill in. You just have to fill in and see, okay, what is the missing little element or particle that's going on in this nuclear reaction. Okay, so just to kind of review, we have alpha, right, in which you're going to be, it's going to involve the helium-4. So you're going to involve this alpha particle, which is helium-4. Helium with a mass of 4, and helium's got 2 protons. Okay, so this is what we call an alpha particle. And then there's beta decay. Okay, in which you get the release of, remember that, electron from inside the nucleus. It's kind of weird to think about, but that's what happens. That's our beta particle. All right, and then you've got fusion, which is fusing. Fusion is, 2 atoms make one big one. And last but not least, you've got fission, which is splitting apart. Splitting atoms apart. Okay. All right, so we're going to go, you guys are going to go through these to figure out, which is which. So let's do the first 3 together, and then I'll give you guys the rest of the time to finish up this whole worksheet. All right, so fill in the missing parts of these nuclear reactions. Alpha decay for radium-226, the most abundant isotope of radium. So radium-226, number of protons is 88. It goes through alpha decay, so we're going to see this alpha particle here, this helium-4 nucleus gets spit out, and what are we left with? Basically, we need to find out, who we are, which element is going to be made. All right, so remember this arrow is always an equal sign. So 2 plus, one way you can think about it is 2 plus what number equals 88? Okay, well, it's going to be 86, right? And 4 here with the mass, 4 plus what number is 26? Well, that's 222. So then we would look at our periodic table and figure out, okay, who is number 86? Because protons give the identity, and you're going to see it's Rn, radon. Okay. All right, the next one is radioactive decay of carbon-14, which is used in radiocarbon dating. Okay, so here we start off with carbon-14. Remember, that tells you the mass. Okay, so this is an isotope of carbon that has a mass of 14. That means 14 minus 6 would be, this one has 8 neutrons in its nucleus. All right, and this is going to go through some kind of radioactive decay, and let's figure out what this means. So in the end, we end up with nitrogen. So we go from carbon to nitrogen. So we have to figure out what kind of particle is spit out of the nucleus. So what number here for, the number of protons plus 7 equals 6. And please be careful, this is a bigger number here than this side, so this has to be -1, right? 1, or -1 plus 7 is 6. And then what number plus 14 equals 14? Well, that's 0. So remember, anytime we have the 0 for mass and the -1 for protons, that's our beta particle, our little electron that's being spit out. Okay? So that one is beta decay. All right, last one we're going to take a look at together is the electron capture by potassium-40, a natural source of radiation in the body. Okay, so electron capture is not one that we focus on, but it is still something that you can still fill in the blanks. It's not, a huge deal. You just have to do the math. It's quite simple. So remember, always look at this arrow as an equal sign, and the top numbers have to equal the bottom numbers. So 40 plus 0 equals what plus 0? Well, that's 40. 19 plus a -1 equals what plus 0? So 19 minus 1 is 18, right? And 18 plus 0 is 18. In fact, this guy is what we call gamma. That's the high energy radiation. So high energy. That's just a symbol for all the energy that gets spit out. So we don't even have to worry about this because this is 0, 0, so it doesn't really apply. Now when we take a look at the periodic table, number 18 is what? It's argon, Ar. So that is our new element that's made when potassium goes through an electron capture. Okay, and it basically captures an electron in the nucleus, which is weird, but there you go. Turns into argon. All right, so that's how you do the rest of the worksheet. You're just going to fill in using your math skills, simple math skills, to make the top numbers equal the bottom numbers on both sides of the arrow. And then you look at your bottom number to figure out who it is on the periodic table. There you go. All right, good luck, have fun, and I'll see you next class.